Okay, and on to metals. So if you think of ionic bonding, now that was a metal and a non-metal. Then we had covalent bonding, which we could see in simple molecular compounds and giant covalent ones, and they share electrons, and that's two non-metals together. And this one is very special. These are metals. Now metals don't really bond to each other. So we can't say it's a bonding of two metals because they don't. You can mix them together in alloys, but you can't actually bond them together. You can't bond a metal and a metal together. So metallic bonding is what we're looking at inside a metal. So it's how does the metal stay together really? What's going on inside it? Not how does it bond. So it's a little bit misleading. So let's have a look at it. So here we've got some copper here, and you've got to think, well, what properties, if we look at what's going on inside it, what are the properties of it, and why does this structure allow the properties to happen? So if we look at it, if we look inside, let's go down to this. This is nice. This is more me. We're going to talk about these now. We'd say let's think of lead. So lead. Now lead's a metal. We understand that is. We could say that inside the lead we've got loads of lead atoms. But we'd be wrong, which is just quite confusing. What we'd have was lead ions. Now what happens is when all the lead atoms are sitting next to each other in our metal, the electrons here, these little electrons that you normally find whizzing around the outside, run off. Fabulous. And you find them, these little electrons, between the atoms, but of course they're not called atoms anymore because they've lost these electrons who've run off, so they're called metal ions. Okay, so that's important. So inside, let's put a little plus on one of them just to show you what I'm on about. Plus. So really they are positive, and there are little electrons here running around the outside are negative. So if you can imagine that it's this positive and this negative that are attracting each other and holding the metal together. So what we call it is a sea of delocalized electrons. That means they're not local to the atom. They've run off and they form a sort of sea, pond in this case, of delocalized electrons. They're sort of between all the atoms, which are not atoms now, remember, because the electrons run off, so they're between the metal ions. So you've got to explain that within a metal you have metal ions held together by the electrons which are delocalized. They come off the atoms and are holding the thing together. They're holding it because there is electrostatic attraction between this positive metal ion and the negative delocalized electron. Okay, so that's what's holding it together. Electrostatic attraction. That's present in ionic bonding, in those ionic compounds where you've got a positive and negative. It's the same thing. Okay, positive and negative. Needs a lot of heat to overcome that, if you remember, in ionic compounds. If not, go back to it. So here it needs a lot of energy to overcome that electrostatic attraction, those high forces of attraction. So they have high melting points and boiling points. I'm going to write it out. Due to high forces of attraction. Okay. There's a lattice again. We can still keep building with it. I can still keep putting lots of other metal ions on it. You can keep going. Other things metals do, what you can bend them. That's because these slide over each other. Look, I can move them about. So therefore they are bendy. What we call is malleable. So, okay, they can conduct electricity because we have electrons here. So conduct electricity because of free electrons. Okay, they conduct heat because of free electrons as well. So high melting and boiling point because of those high forces of attraction. We've got malleable because we can move the ions, and they conduct electricity and heat because